Just check the audio is working. Yes. All right, great. So tonight going to do another quick little paper reading. So today we're going to be looking at, let me pop open the other screen. There we go. So we're going to be looking at this paper, which is from Neurips this year. Neurips is a kind of like the biggest machine learning conference. This paper is called Overparameterization Improves Robustness to Covariate Shift in High Dimensions. So seems like a pretty interesting paper discussing essentially the relationship between how many parameters are in like a machine learning model and how robust that model is to covariate shift, which covariate shift is when there's a difference between like the data that you're training with and the data that you're testing on in a machine learning setting. So we're going to try to go through this paper. This one's a little bit longer than the other night, just since this is kind of like the first time I'm reading, and I kind of recommend this for other people who are reading papers as well. I'm kind of just going to like skim through the math. I'll try to like understand what they're trying to do, but there's a fair number of equations in here that look like they could be take a little bit of time to really, if I wanted to dive into and understand 100%. So I'm not going to try to get too bogged down in this sort of stuff. Just kind of believe the authors for the first pass, and if this becomes a very important paper for me, then I'll come back and really understand everything. Okay, so with that, let's go ahead and get to it. All right, my mouse, there we go. So a significant obstacle in the development of robust machine learning models is covariate shift, a form of distribution shift that occurs when the input distributions of the training and test sets differ while the conditional label distributions remain the same. Despite prevalence of covariate shift in real-world applications, a theoretical understanding in the context of modern machine learning has remained lacking. In this work, we examine the exact high-dimensional asymptotics of random feature regression under covariate shift and present a precise characterization of the limiting test error, bias, and variance in the setting. Our results motivate natural partial order over covariate shifts that provide a sufficient condition for determining when the shift will harm or even help test performance. We find that overparameterized models exhibit enhanced robustness to covariate shift, providing one of the first theoretical explanations for this ubiquitous empirical phenomenon. Additionally, our analysis reveals an exact linear relationship between the in-distribution and out-of-distribution generalization performance, offering an explanation for this surprising recent observation. Okay, so what I get from the abstract here is, like we said before, there's they're talking about the covariate shift, which is how the network that's trained on one distribution will perform on a sort of distribution that has some statistics that are different, and that statistics is kind of a catch-all term here. So they're saying that they're going to present high-dimensional asymptotics. So I guess this means that they're going to kind of say, like, try to give kind of scaling law for how number of parameters sort of affects the generalization ability or this robustness to this shift. Our results motivate natural partial order over covariate shifts. Okay, I'm not sure what they mean by partial order here. I know what a partial order is, but I don't know exactly what they mean. That they're going to provide a partial order over the test performance, but that's fine. Hopefully we'll get a better example of that. And they say, okay, so we find that overparameterized models exhibit enhanced robustness. So this is obviously true. If you've done any machine learning, neural nets have like an insane number of parameters, and they seem to be amongst the best sort of generalizable models to lots of different sorts of inputs. Okay, so hopefully we can answer the kind of couple questions we had from the abstract, and let's keep going. Theoretical justification for almost all machine learning methods relies upon the quality of the distributions from which the training and test data are drawn. Nevertheless, in many real-world applications, this equality is violated. Naturally occurring distribution shift between training data and data encountered in deployment is the rule, not the exception. Even non-adversarial changes can uncover the surprising fragility of modern machine learning methods. Such shifts are distinct from adversarial examples, which require explicit poisoning attacks. Rather, they result from mild corruptions ranging from the changes of camera, angle, or blur, to subtle, unintended changes in data acquisition procedures. Moreover, this fragility limits the application of deep learning in certain safety-critical areas. Empirical studies of distribution shift have observed several intriguing phenomenon, including linear trends between model performance on shifted and unshifted test distributions, dramatic degradation in calibration, and surprising spurious inductive biases. Theoretical understanding of why such patterns occur across a variety of real-world domains is scant. Even basic questions, such as what makes certain distributions shift likely to hurt or help a model's performance, and by how much, are not understood. One reason that these phenomena have eluded theoretical understanding is that there is often a strong coupling between model and distribution, implying that the effect of a given shift cannot usually be understood in the model-agnostic way. Another reason that satisfactory explanations have remained lacking is that the go-to formalism for studying generalization in classical models, namely uniform convergence theories, uniform convergence theory may be insufficient to explain the behavior of modern deep learning methods, even in the absence of distribution shift. Indeed, classical measures of model complexity, such as various norms of the parameters, have been found to lead to ambiguous conclusions. Okay, so just summarizing here, they just say this is kind of a well-known phenomenon, like we said at the end of the abstract. There's adversarial examples, which kind of cause a distribution, like they're like tuned to the network to make covariate shifts that specifically make the network like do bad. Whereas in the real world, these things kind of happen at random, so they're not like tuned to make the network do bad. But regardless, you can see that there's this happens a lot, in machine learning models, that kind of small changes in the input data that kind of a human wouldn't even notice, the computer like goes crazy when you give them those examples. And then they say it's kind of hard to study this phenomenon, specifically because it often depends not only on the data but also on the model. And there's this uniform convergence theory, which I actually am not familiar with, that they say is insufficient in deep learning. All right. In this paper, we follow a different approach, instead focusing on worst-case bounds for generic distributions. We study average case behavior for narrowly specified distributions. While this change in perspective sacrifices generality, it allows us to derive more precise predictions, which we believe are necessary to fully capture the relevant phenomenology. We study a specific type of distribution shift called covariate shift, in which the distributions of the training and test covariates differ. While the conditional distribution of the labels given the covariates remains fixed. So a specific type of distribution shift called covariate shift, in which the distributions of the training data and test covariates differ, while the conditional distribution of the labels given the covariates remains fixed. Using random matrix theory, we perform an asymptotically exact computation of the generalization error of random feature regression under covariate shift. The random feature model provides a useful testbed to 1, investigate the interplay between various factors, such as model complexity, label noise, bias, variance, and covariate shift. 2, rigorously define a model-agnostic notion for the strength of covariate shift. And 3, provide a theoretical explanation for the linear relationships recently observed between in-distribution and out-of-distribution generalization performance. Okay. So basically not a whole lot new. They're just telling us what they're gonna accomplish. Okay, so contributions. Our primary contributions are 1, provide a model-agnostic partial order over covariate shifts that is sufficient to determine when a shift will increase or decrease the test error in random feature regression. Compute the test error, bias, variance, bias and variance of random feature regression for general multivariate Gaussian covariates under covariate shift in the high dimensional limit. Prove that overparameterization enhances robustness to covariate shift, and that this error, bias, and variance are non-increasing functions of the number of excess parameters, and deduce an exact linear relationship between in-distribution and out-of-distribution generalization performance, offering an explanation for this surprising recent empirical observation. Okay, so actually one thing I want to quickly check out is get a stronger definition of this. Yeah, because I've seen this used in this kind of in this sort of, I guess, more colloquial way, which is just that the distribution of input shifts compared to the live environment. But these guys kind of seem like they were talking about a very specific sort of shift where something is held constant. Okay, I don't want to spend a ton of time on this. I think they might clear it up as we read a little bit more. But they said, just specifically again, distributions of training and test covariates differ, while the conditional distribution of the labels given the covariates remains fixed. Not really sure what they mean by this, but let's keep going. Related work, there's extensive literature on empirical analysis of the distribution shift in all of its myriad of forms, ranging from domain adaptation to defenses against adversarial attacks to distributionally robust optimization, among many others. Interestingly, for naturally occurring distribution shifts, standard robustness interventions provide little protection. Indeed, empirical risk minimization on clean, unshifted training data often performs better than out-of-box benchmarks than more sophisticated methods. One of the most striking observations in this context of natural distribution shifts is that model robustness improves the classifier's accuracy. For example, if a classifier's accuracy increases by 1% on unshifted CFAR10 tests, this tends to increase its accuracy by more than that on CFAR 10.1, a dataset with a natural distribution shift. Moreover, such linear trends between unshifted and shifted measures of error have now been observed in several contexts. Okay, so they're just saying generally if your model does better even on unshifted data, it tends to also generalize better to shifted data. Yeah, that is actually really interesting. Because you would think like you could do this with overfitting, but oh, okay, well, I guess you can't be overfitting since you're talking about the classifier's test accuracy, presumably. Okay, the number of theoretical works studying the impact of distribution shift on generalization is far smaller. One pioneering work proves that VC dimension-based error bounds for classification that are augmented by a discrepancy measure between source and target domains. Okay. While another demonstrates a similar class of uniform convergence-based results in the setting of kernel regression. Recent work shows that learning domain invariant features is sufficient to guarantee generalization when the class conditional is insufficient, to guarantee generalization when the class conditional. This sentence is weird. When the source domain gradually shifts towards the target domain, non-vacuous margin-based bounds for self-training can be established. In 40, assumptions based on model similarity are used to explain why classifiers exhibit linear trends between their accuracies on shifted and unshifted test sets. Our technical tools build on a series of works that have studied the exact high-dimensional limit of the test error for growing class of model families and data distributions. In the context of linear models, recent work analyzes ridge regressions for general covariances and a general non-isotropic source condition on the parameters which generate the targets. Extending earlier work by studying minimum norm interpolated least squares and ridge regression in random design settings, the non-isotropy of source parameter effectively induces a shift on the bias term of this model, but the phenomenon is distinct from the covariate shifts we study here. Beyond linear regression, random feature models provide a rich but tractable class of models to gain further insights in the generalization phenomenon. These methods are of particular interest because their connection to neural networks with a number of random features corresponding to the network width, or model complexity. Because they serve as a practical method for data analysis in their own right. In this context, a precise characterization of the gaps between uniform convergence and asymptotic test error as a function of sample size and number of random features can be derived. From the technical perspective, our analytic techniques build upon these works and a series of recent results stemming from the literature on random matrix theory and free probability. Okay, so I really didn't understand anything in here in these last two paragraphs. Which is fair. I don't know that much about I don't know that much about this type of, about the theory behind this type of system. So, I guess that makes sense, but just trying to maybe summarize as best as I can. There's been work on VC dimension-based error bounds for classification. And kernel regression. Okay, so this is that uniform convergence theory they were talking about before. Kernel regression, I think, is means that you have a specific function that you're fitting instead of like a neural net. Domain invariant features is insufficient to guarantee generalization. When the source gradually goes towards the target, there's some bounds for self-training. Okay. Just going to move on. Don't want to spend too much time here. There's obviously tons of references and stuff that you can go down these rabbit holes. All right, so preliminaries. Problem setup and notation. As in prior work studying random feature regression, we compute the test error in high-dimensional proportional asymptotics, where the data set size m, input feature dimension n0, and hidden layer size n1 all tend to infinity at the same rate. Okay. So they define phi, which is the input feature dimension over the number of examples, and psi, which is the input feature dimension over the hidden size. And they hold those fixed. We refer to phi over psi as the overparameterization ratio, which is the limit of the hidden layer size over the number of examples, and characterizes the normalized complexity of the random feature model. Okay. Interestingly, in this high-dimensional limit, the conditional distribution of a linear labeling function is asymptotically equivalent to a wide class of nonlinear teacher functions. With this in mind, we consider the task of learning an unknown function from m independent identically distributed samples where you have xi, yi, so these are going to be your input features, these are going to be your labels, where the covariates are Gaussian. So so they say that all of the input features are Gaussian in nature, so they're distributed as a Gaussian with a positive definite covariance matrix sigma. And the labels are generated by a linear function parameterized by beta, which is sampled from our n0. So n0 was the input feature dimension. Okay, yeah, right. So they're just saying the labels are generated by a linear function. Okay. Huh. I'm not sure what this means that the labels are generated by a linear function. They mean like the ground truth labels? So that seems to be like a huge restriction to the types of problems they're working on, which might be the case for this paper anyway. But, in general, if the function was linear, then you wouldn't really need a neural net. But anyway, they're going to say that the y is equal to, beta.x with some normalization plus some noise. So we study the class of prediction models defined by kernel ridge regression using unstructured random feature maps. The random features are given by a single layer fully connected neural net with random weights, given a set of training data, x, which is this vector, and a prospective test point, x, other kind of x. The random feature embeddings of the training and test data are given by f, which is this function sigma acting on w times x, again normalized, and little f, which is w times that specific x. Okay, so they say consider having a random set of features in this W matrix. If you have a training set with all these points x1 through xm, and you have a single test point, which they're calling x, they define this function big F, which is the thing that you're fitting, sigma, which is, I guess, this neural net. They say single layer fully connected neural net. So that's just like basically a bunch of logistic regressions. So yeah, they define big F as the outputs of those networks for the test data, the training data, and little f as the output for that test point. For random weight matrix W, which is in n1 cross and R n1 cross n0, with IID, standard Gaussian entropys, and an activation function sigma from R to R applied element-wise. The induced kernel is given by this thing. Okay. And the model's predictions are given by y hat, which is y k inverse kx, where y is the list of labels, and these kernels. So I'm not really sure Ridge regression, if I remember correctly, is just like basically linear regression with a weight decay term. So I do believe that there's a what is it called? It's like a closed form solution to this problem. So I guess what they're saying here is that K is the closed form solution, or at least used to come up with the closed form solution. I'm not exactly sure what kernel means in this context. But okay, so owing to the implicit regularization effect of nonlinear feature maps in low noise settings, the optimal value of gamma can sometimes be negative. For simplicity, we nevertheless make the standard assumption that gamma is greater than 0, and we emphasize our techniques readily accommodate negative values. Though we emphasize. Our central object of study is the expected loss for a data point x, which is taken from a normal distribution with mean 0 and variance sigma star, where sigma star may be different from the training covariance, which was just sigma. The test error without label noise on the test point is given by the expected value of, this is just sigma, and this is y hat, right? So yeah, so they're saying that this k is somehow, okay, I guess these k's are needed to basically find that closed form solution for the training. For training. And so they're just, that's why they've constructed this k. And so yeah, they're just saying that, the error is just the expected value of the outputs of the neural net, which is this piece, and the true values here. Okay, no, I must have that wrong, because yeah, these are like the true labels for x. Okay, so for some reason you can write the true labels of x in terms of these functions. Okay. I'm not sure why they're doing that. And then they break this apart into two pieces where you have the expected value over x and beta of the expected value of the expected value of the true labels minus the outputs of the neural nets squared. Okay, so yeah, they're just breaking apart the error into these two terms, which is a standard thing people do in stats. So one of the terms is going to be, they're like two different types of errors or something. We overlay definition, regularization. Okay. So V variance. Yeah, right. So this is like I think this is called a bias variance decomposition or something, if I remember correctly. Okay, anyway, but there's just like two different types of errors. Where inner expectations defining the bias and variance are computed over W, X, and Y. We decompose the training and test covariance matrices into eigenbases as sigma equals this sum, and sigma star equals this other sum, where the eigenvalues are in non-decreasing magnitude. We define overlap coefficients Ri to measure the alignment of sigma star with the nth eigendirection of sigma. In particular, Ri is the induced norm of Vi with respect to sigma star. We use the trace to denote the dimension normalized trace for a matrix, which is in for n by n matrix, and use a double bar infinity and a double bar f to denote the operator norm and Frobenius norm of the matrix respectively. Finally, we use delta x to denote the Dirac delta function centered around x. Assumptions. Regularity assumptions on the spectra of sigma and sigma star are necessary to state the limiting behavior of the system. As in 66, it is not. Okay. Is that working again? Yep. All right. Sorry about that. So we have lambda here is given by this thing. So these overlap coefficients decompose training and test covariance matrices into eigenbases. Okay, so lambda eigenvalues of the training covariance matrix and lambda star eigenvalues of the test covariance matrix. Okay. And then R so sigma star is the variance of the test set, if I remember correctly. Okay, and then these V's are the rows of the covariance matrix of the training set. Okay, so we define the empirical joint spectral distribution as this thing and assume it converges in distribution to some mu, a distribution on r squared plus, r2 plus, sorry, as n goes to infinity. Converges in distribution to some mu. We refer to this mu as a limiting joint spectral distribution and emphasize that this defines the relevant limiting properties of the train and test distributions. Additionally, we require that the limit of the supremum and 0 of the max of epsilon infinity, epsilon star infinity less than c for a constant c. Often we use lambda r for random variables sampled jointly from mu and denote the marginal of lambda under mu with mu train. The conditional expectation E r lambda is an important object in our study. We frequently overload notation E r lambda to view it as a function of lambda. And we assume the following for simplicity. That mu is either absolutely continuous or a finite sum of delta masses. Moreover, the expectations of lambda and r are finite. When eigenspaces of sigma and sigma star are aligned and Ri equals lambda I equals phi lambda I for some smooth function phi, the support of the LJSD degenerates. Here, assumption 1 is essentially equivalent to assuming the empirical spectral distribution of sigma converges in distribution to some mu train, which is standard assumption in the regression literature. One special case of note is when there is no shift, i.e. phi is the identity, in which case LJSD degenerates to mu0, defined by mu train delta lambda r. In other words, lambda is mu0 for lambda is mu train. As our analysis will eventually take place in high dimensional limit, we further define the asymptotic scales of the training and test covariance as S equals the limit n0 to infinity of the trace of the covariance matrix, the training covariant matrix, expectation value of mu over lambda. Okay, so I just want to quickly refresh myself. Seems like these lambdas are really important, which again, yeah, eigenvalues of the covariance matrices. Okay. Throughout this paper, we also enforce the following standard regularity assumption on the activation functions to ensure the existence of the moments and derivatives we compute. The activation function sigma r to r is assumed to be differentiable almost everywhere. We assume that sigma x, sigma prime x, the absolute, that both the absolute value of sigma x and sigma prime x is less than c0 e to the c1x for constant c0 and c1. So I guess they're just assuming that the neural net, that the activation functions are just bounded, essentially. And the derivatives are also bounded. Okay, so that's assumption 3. Assumption 2, mu is either absolutely continuous or a finite sum of delta masses. Moreover, lambda and r are finite. So, right. So they say finite overlap coefficients, which are like these products between the covariance matrices and eigenvalues of the covariance matrix. And how do I interpret this thing? So it's like a delta function of the eigenvalue with this r thing. Where r is basically like the length of the eigenvectors. Or no, this. Okay, it's kind of a weird object. You got one row from the covariance matrix of the test set, one row from the covariance matrix of the training set. You take their dot product and square it, and then you have a eigenvalue from the test set there. That's the sum over all the test set eigenvalues. So it's basically like how much does the covariance matrix overlap with each. Okay, yeah. So it's like weighted by the eigenvalues of the test covariance matrix. How much does each row of the training covariance matrix overlap with the row of the test covariance matrix? So I guess it's a kind of like matrix similarity thing. I'm not sure if there's some deeper meaning if I knew stats better. Okay. All right. A simple family of diatomic distributions. As the above assumptions allow such general class of covariance structures, it is useful to consider our results in the context of a simple family of distributions that readily admits a simple interpretation. Definition 2.1. For alpha greater than 1 and theta is a real number, we'll find the family of alpha theta diatomic LJSDs with theta power law shift as mu diatomic, 1 over 1 plus alpha with a delta function of alpha and c alpha to the theta plus alpha over alpha plus 1 and delta of alpha inverse c alpha to the minus theta, where c is a normalization constant chosen such that the expectation value of this thing with respect to r is 1. Note that mu diatomic is the limit of alpha if I is equal to j, and it's less than the I think n0 was the dimension. Input feature dimension, yeah. Input feature dimension over 1 plus alpha. Alpha inverse. Okay, alpha is just some number. Okay, yeah, I don't really understand this at all. But let's see if we can get pi without it. This simple 2-parameter family of distributions captures the fast eigenvalue decay observed in many datasets in machine learning, for which the covariance spectra are often dominated by several large eigenvalues and exhibit a long tail of many small eigenvalues. Note that the trivial case of alpha equals 1 yields an identity covariance with no shift. For the non-trivial setting, alpha greater than 1, the exponent theta parameterizes the strength of the shift in an intuitive way. When theta equals 1, there is no shift. When theta is less than 1, alpha to the theta is less than alpha, so the large eigendirections of the training distribution are suppressed in the test distribution, suggesting that the shift makes learning harder. When theta is greater than 1 and alpha to the theta is greater than alpha, so large eigendirections of the training distribution are further emphasized in the test distribution, suggesting that the shift makes learning easier. Okay, this might be something we can use to help us understand some of these definitions. They define alpha somewhere else, because here it just seems like they're just like choosing an alpha. Yeah, I don't know if alpha has some like standard definition in this field that I'm not aware of. Can I see it from you? 1 over n0 delta. Yeah, I'm not really sure what alpha is. At least it's not immediately obvious to me. What they say, this problem's only non-trivial when alpha is greater than 1. In that case, theta parameterizes the strength of the shift in an intuitive way. When theta is 1, there is no shift. When theta is less than 1, alpha to the theta is large, so eigendirections of the training distribution are suppressed in the test distribution. So basically, they're saying for some reason when alpha to the theta is less than alpha, you have, you basically learn different eigendirections. Whereas when theta is greater than 1, you learn the most important eigendirections of the test distribution. I'm not really sure why that's true with this notation. I still don't really know what alpha is, but okay, let's just keep moving on. We first consider the relatively simple case of Ritzless linear regression, which will help build some intuition for more general analysis of random feature regression in section 5.1. Assuming the labels are generated by linear models defined above, yi equals b dot x. The estimator is given by b hat, which is this thing. This I do recognize as the solution for just linear regression. The betas or the this exactly what they're saying. So this is just how you, if you have the x's are the input variables and y is the labels. It's like a matrix of those. And the task risk has the following simple form. For fixed dimension n0 and sample size m greater than n0 plus 1, the test error of linear regression is given by this thing. Under assumption 1, as n of them go to infinity and phi goes to n over m, which is fixed, or phi is fixed. The error from linear regression goes to this function, which is sigma squared epsilon times phi over 1 minus phi times the expectation value over mu of r over lambda. One immediate question is whether a given shift will increase or decrease the test error relative to the expectation value, while the precise answer is of course determined by the value of the trace. It is useful for subsequent analysis to develop an understanding of the individual contributions to this term. Similar decompositions for the test error into eigenspaces have proven useful in a variety of other contexts, e.g. in 42 and 4. We begin with a specific example in the setting of finite dimensional analog in definition 2.1. For the definite form alpha theta, diatomic density defined in equation 10, the test error of linear regression is given by this thing. So dd theta of E is less than 0, which implies that the expected value of linear regression sigma 1 is less than sigma 2. Whenever theta 1 is greater than theta 2, in accordance with the discussion section 2.3, follows from 10 that the condition theta 1 greater than theta 2 not only implies this trace thing, but that the ratios of overlap coefficients form a non-decreasing sequence. It is in this condition involving all eigendirections that we will generalize to nonlinear random feature setting in section 4. The following proposition captures the essence of these considerations in the context of linear regression. See section A4 for the proof. Okay. I'm going to try tracking along a little bit further. I think I've completely fallen out of my depth at this point, and I'm not really getting anything. But let's see if we can go a little bit further and maybe start to get some traction again. Okay. Whereas the alpha theta diatomic LJSDs explicitly enforce the trace normalizations. Proposition 3.2 provides sufficient conditions for the ordering of test errors and non-unit traces. The fact that the expectation value scales linearly with the overall scale of sigma star is a unique feature of linear regression and does not generalize to nonlinear random feature settings. We will return to this discussion in section 4. Okay. So overall, what they're trying to say in this section is what? They say, okay, if we look at linear regression, the test set error is given by this, which is the trace of the covariance matrices. So you have the test covariance matrix times the inverse of the training covariance matrix. Times this factor, which is the number of the input dimension over the number of samples minus the input dimension minus 1. And you have this factor sigma epsilon squared up front. And they're saying you can also write this trace as 1 over n0 times the sum of this Ri over lambda I, where the Ri was that weird overlap thing, and lambda were the eigenvalues of the training covariance matrix. So they say they can test whether a given shift will increase or decrease the tested error relative to the training set error. The precise answer, they say, is determined by this thing. So they write this again. They just basically replace this sum here with this term. Which is also the same as that trace. And they say W is 1 over n naught times the floor n0 1 plus alpha. And they say, what if we look at the derivative of this with respect to theta? They get this thing, which they say has to be less than 0. Okay, so they're saying that if you have two different thetas, which I guess theta is ultimately like the shift somehow. Yeah, so when theta is 1, there's no shift. When theta is less than 1. So larger theta means means you should do better on the test distribution, if I remember correctly. Or I'm staring at it, I don't need to remember. So are they just seeing that this bears itself out here? So if we get a larger theta, right. It's going to show that the errors, I guess, should go down. So theta 2's error should be lower. Sorry, theta 1's larger here. So theta 1's errors should be lower. But ratios of the overlap coefficients form a non-decreasing sequence. So these overlap ratios, again, were the amounts that each eigenvector of the training set's covariance matrix overlaps with the test set's covariance matrix. So it's just saying that you get more training set in your test set. Not that you get more training set in your test set, but the eigenvectors of the training set covariance matrix overlap more with the eigenvectors of the test set covariance matrix, which I guess means that you're going to fit the test set better, ultimately. Okay, proposition 3.2, let R1 and R2, Ri1, Ri2 denote the overlap coefficients of some training sets 1 and 2 relative to the, some test sets 1 and 2 relative to the training set. If the trace of the covariance matrix for set 2 is greater than the trace of the covariance matrix for set 1, then the ratios Ri1 and Ri2 form a non-decreasing sequence. In the setting of proposition 3.1, the error for set 2 is greater than the error for set 1. I'm not sure if they mean this trace here, but I think they're just saying basically the same thing that we saw before. All right, when alpha, theta, diatomic LJSDs explicitly enforce the trace normalizations, Prop 3.2 provides sufficient condition for the ordering of test errors for non-unit traces. The fact that blah blah the test error scales linearly with the overall scale of sigma star is a unique feature of linear regression. Oh, okay. No, so they do literally mean these traces. Okay, yeah, I guess they're just saying in linear regression, right, high variance leads to high error in linear regression, right? That's actually pretty obvious. Okay. So let's see section 4. We got some pictures coming up. Okay. Deriving conditions on whether a shift will hurt or help a model's performance is crucial to building an understanding of covariant shift. motivated in part by the results above for linear regression and in part by the results for random feature regression that we present in 5.3. We introduced the following definition of shift strength, which is a direct generalization of the conditions in proposition 3.2. 3.2 was this thing about linear regression. Let mu1 and mu2 be the LJSDs with the same marginal distribution of lambda. Denote mu train if the asymptotic, denoted by mu train. If the asymptotic overlap coefficients are such that the expectation value over mu1 of r given lambda over expectation value mu2 of r given lambda is non-decreasing as a function of lambda on the support of mu train, and the expectation of value of r with respect to mu1 is less than the expectation value of r with respect to mu2. We see that mu1 is easier than mu2, or that mu2 is harder than mu1. And we'll write that mu1 is less than mu2. Comparing against the case of dose shift mu0, we say mu1 is easy when mu1 is less than mu0, and hard when mu1 is greater than mu0. Okay. A priori, there's little reason to hope that such a model-independent definition of shift strength would adequately characterize a shift's impact on its total error, bias, or variance of a given model. Even for the relatively simple case of random feature kernel regression, the nonlinear feature maps of equation 2 would seem to inextricably couple to the covariance distribution of the model. Nevertheless, we show in section 5.1 the coupling between the model and shift simplifies considerably in the high-dimensional proportional asymptotics. It is characterized by a handful of constants that depend solely on the overall covariance scale ER, and a collection of functionals of mu, whose magnitude can be bounded in terms of the ratio E mu r given lambda over E mu 0 r given lambda. The conditions that definition 4.1 place on E mu r and E mu r given lambda over E mu 0 r given lambda can be augmented by various constants on the model to derive bounds on how the total error and bias will respond to a shift of given strength. This perspective introduces considerable complexity, and we present the details of the analysis elsewhere. In this work, we focus on a simpler surprising result by merely normalizing the scales of the covariate distributions, i.e. enforcing that S equals S star. Definition 4.1 provides a model-independent definition of the shift strength that determines how random feature models respond to shifts of different strengths. This observation motivates the following assumption. The training and test covariance scales are equal. E mu lambda equals E mu r, i.e. S equals S star. We emphasize that assumption 4 reflects common practice for many models and data modalities, as pre-processing techniques such as standardization are ubiquitous in many architectural components, such as layer norm, batch norm, and achieve similar effects. Okay. Covariate shift and random feature kernel regression. Main result. Our main result characterizes the high-dimensional limits of this test error, bias, and variance of the nonlinear random feature model of section 2. Before starting them, we first introduce some additional constants that capture the effect of nonlinearity, sigma. For z, which is samples from a normal, define eta as the variance of sigma of z, rho as 1 over the expectation value of z times sigma z, squared, normalized by s, and c, if I remember, is s times rho, and then omega is s times eta over xc minus 1. Our results also depend on the covariance spectra through two sets of functionals mu. IAB of x is phi times the expectation value of mu, lambda a, phi plus lambda x to the minus b, and I star is the same thing, but with an r in there, and a goes minus 1. So this section, okay. So theory of 5.1. Under assumptions 1, 2, 3, and 4, as the input size, hidden size, and number of examples go to infinity, the test error E sigma star converges to E mu, which is B mu plus V mu, with bias B mu and variance V mu, given by bias is phi times I star 1, 2, and V is this complicated mess. Okay. Where x is unique non-negative real root. Okay. Numerical predictions from 5.1 can be obtained by first solving the self-consistent equation for x by fixed point iteration, and then plugging the results into the remaining terms. Figure 1 shows excellent agreement between these asymptotic predictions and finite simulations. Okay. Yeah, I think I am going to call it for this evening at least. That's been a little over an hour of streaming. And not sure if I'm going to come back to this one. Kind of don't think I have enough of the stats background to really get where we're going. But so far, kind of got the idea that they can maybe show that the these eigenvectors of the covariance matrices of the inputs are really important, and basically covariate shift is not always a detrimental thing. Sometimes it can cause the certain eigenvalues to be sort of overrepresented from the training set, whereas in the kind of typical case where you think it's bad, it causes them to be underrepresented. And this is seems like a fully theoretical paper. I was hoping that they would do some experiments at some point. I guess they actually do here. They're talking about ImageNet. But all right, yeah, thank you guys for watching, and yeah, I appreciate it.